Capacitor is a battery that will transfer charge from one plate to the other until the voltage produced by the charge buildup is equal to the battery voltage. And capacitance is typified by a parallel plate arrangement and is defined in terms of charge storage. The formula is C is equal to Q over V, which is coulomb over volt. If we're talking about the unit, it's about coulomb over volt length equals to Farad, where Q is the magnitude of charge stored in each plate and V is voltage applied to the plates. Capacitance is Farad, which is named after Michael Faraday.
There are 4 types of capacitors: the film capacitors, the electric capacitors, ceramic capacitors, and electrolytic capacitors. Film capacitors are most commonly available of all types of capacitors, consisting of a relatively large family of capacitors, with the difference being in their dielectric properties. Electrolytic capacitors are generally used when very large capacitance values are required. Instead of using a very thin metallic film layer for one of the electrodes, a semi-electrolyte solution in the form of a jelly or paste is used, which serves as a second electrode, usually the cathode. Ceramic capacitors, or disc capacitors, are made by coating 2 sides of a small porcelain or ceramic disc with silver and are stacked together to make a capacitor. Ceramic capacitors have values ranging from a few picofarads to 1 or 2 microfarads, but their voltage ratings are generally quite low. Ceramic types of capacitors generally have a 3-digit code printed onto their body to identify their capacitance value in picofarads.
The formula for capacitors in parallel is C total is equal to C1 plus C2 plus C3 plus Cn, where n is the number of capacitors. Capacitors in series is the formula is C total is equal to 1 all over 1 over C1 1 over plus 1 over C2 plus 1 over C3 plus 1 over Cn. In a capacitor, the formula used is U is equal to 1/2 QV is equal to 1/2 CV squared is equal to Q squared all over 2C is equal to QV over.
The simplest form of capacitors consisting of 2 parallel metal plates where they have the same area A, separated by a distance D, a charge positive Q on one plate and a charge negative Q on the other plate. The formula for parallel plate capacitors is C is equal to epsilon naught A over D, where epsilon naught is constant and the value is 8.85 times 10 to the negative 12, and A is the total area of one plate and D is the distance between the 2 metal plates. Or C is equal to A over 4 pi kd, where K here is constant and its value is 9 times 10 to the 9.
So now, let's talk about capacitors with dielectrics. A dielectric is an inductor placed between 2 parallel metal plates. It is sandwiched between them. What happens here is that 2 parallel metal plates create an electric field. And in between this, we place the dielectric, of course. So what happens here is that the dielectric makes the charges polarized. So it increases the capacitance. We can solve the capacitance by the formula C is equal to kappa E naught A all over T. So the Greek letter kappa stands for the dielectric constant, and it differs from one material to another. But it sure is guaranteed that the dielectric constant is positive.
The capacitor can be charged by connecting one plate to the positive terminal of a battery and the other to the negative terminal. The electric field produced by the battery causes electrons to flow towards the positive terminal of the battery and away from the negative terminal. One will be positively charged and the other will be negatively charged. The insulating material keeps the charges from crossing over from one plate to the other and allows the capacitor to store electrical charges. If it is disconnected from the battery, the charges will remain stored in the capacitor until it is connected to another electric unit. The capacitance of the capacitor tells you how much charge it can store when connected to a particular battery and is measured in units of farads. The capacitance C of a capacitor can be determined by measuring the amount of charge stored on plate Q when it is connected to a battery with a certain voltage V. C is equal to Q over V. Uses of capacitors. Capacitors are used in many devices that require electric energy to be released quickly, like camera flashes and computer keyboards. They are also used in circuits that are designed to filter and amplify electronic signals. Energy. To move a small amount of negatively charged from the positive plate to the negative plate of a capacitor, an external agent must do work. This work is the origin of the energy stored by the capacitor. Delta V is equal to Q over C. If Q is equal to 0 and work is done to add charge until small q is equal to big Q, the total work required is U is equal to 1/2 big Q delta V. Equivalent capacitance. Like resistors, capacitors can be arranged in series or in parallel. The rule for adding capacitance is the reverse of adding resistance. Capacitors in series add like resistors in parallel, and capacitors in parallel add like resistors in series. For two capacitors in series, 1 is over C total is equal to 1 over C1 plus 1 over C2. For two capacitors in parallel, CT is equal to C1 plus C2.
Series and parallel.
For example, if we connected a capacitor to a 4-volt battery and measured that it stored 12 coulombs of charge, using this formula, its capacitance would be 3 Farad.
I've got ability in a circuit to collect energy in an electric field in the form of electric charge, and I discharge faster compared to batteries. Farad's the SI unit of my SeriQ equals Q over V. It's the ratio of the E charge to voltage. Ooh, capacitors in parallel don't work the same within series. They work with different equations. Don't mess up when we can fix the problem of yours. That's why we made use of this cutting code. SeriQ series has equal charge. So just imagine an electric circuit with capacitors in series. Find capacitance of the capacitors in series. They just have equal charge, so you only need the voltage. Then manipulate equation and solve it. Can't stop the feeling. Equals 1/2 QV. U equals 1/2 QV. Ooh, parallel plates are made up of two parallel metal plates. They have same area, separated by D. Its equation is E not A all over D. Farad's the SI unit of my C is equals Q over V. It's the ratio of the E charge to voltage. Ooh, capacitors in parallel don't work the same within series. They work with different equations. Don't mess up but we can fix the problem of yours. That's why we made use of discarding codes. Bar V parallel equal volts. So just imagine, just imagine, just imagine an electric circuit with capacitors in parallel. Find capacitance of the capacitors in parallel. They just have equal voltage. You only need the charge and then manipulate equation and solve it. Can't stop the feeling. U equals 1/2 QV. U equals 1/2 QV. U equals 1/2 QV. U equals 1/2 QV. I can't stop the. I can't stop the. I can't stop the. I can't stop the. Can't stop the an electric circuit with capacitors in series. Find capacitance of the capacitors in series. They just have equal charge, so you only need the voltage. Then manipulate equation and solve it. An electric circuit with capacitors in parallel. Find capacitance of the capacitors in parallel. They just have equal voltage. You only need the charge and then manipulate equation and solve it. Break it down.